Now, let's look on the elementary row operations and the determinants. So in this video, we will talk about the effect of the elementary row operations on the determinants. So the elementary row operations has the effect on the determinants as follows. So if we swap the rows in the elementary row operations, as you can check, if we swap the rows, then the determinant of the new matrix after this operation is equal to the determinant of the original matrix but negative times. Okay, so whenever you will swap the rows, the determinant will be negative. This is the rule. You have to memorize. Look at the second rule. The second rule is if you multiply any row by any scalar k, so Ri is any row and k is any scalar matrix, so you have a matrix and you multiply any row with any scalar, then the determinant of the new matrix will be equal to this k times the determinant of the original matrix. This is the second rule. And the third rule is if you swap any row, if you interchange any row by the row and the product of another row with a scalar, then the determinant will have no change. Okay, so for example, here you have a matrix. Then you can check that this is row 1, this is row 2, and this is row 3. The first property says that if I interchange any two rows from this matrix, for example, if I interchange row 1 and 3, then the determinant will be negative. Okay, so let's check. Suppose that the determinant of this matrix is determinant of A is, for example, D. Then if I swap any two rows, for example, row 1 with 3, then what will happen? Then the rule says the determinant of this A prime, this is new matrix, it is called A prime, is equal to negative D. Because the determinant of A was D, then we have swapped the rows. After swapping, the determinant will be negative of the exact original determinant. So this is the first rule. Look at it again. It says whenever you swap the rows, Ri with Rj, that means any row with any other row, if you swap, then the determinant becomes negative. Similarly, if you multiply any row of this matrix with any scalar, then the new determinant will be obtained by multiplying the determinant of this matrix with that scalar. For example, this is the matrix, and if you multiply its any row with any scalar, for example, take the scalar 5 and multiply 5 with, for example, R2. With any row you can multiply. If you multiply any scalar by any row, then what will happen? The first row and the last row will be as it is, but the second row will be the product of 5. So the first entry will be negative 5. The second entry will be 15. The last entry will be 25. So this is the new matrix. So now if I take the determinant of the first, for example, I have no calculations, but suppose that the determinant of the first matrix is D, then the determinant of this new matrix is called A prime. So this is A prime. So the determinant of this A prime would be this 5 times D. 5 times the original matrix. Why? Because I have multiplied a row by a scalar 5. If you multiply this row by any other matrix, then the same thing can happen. So the very first consequence is, if two rows of the matrix are identical, then the determinant of the matrix is 0. Look at the proof. In order to prove this consequence, we suppose that we have a matrix and whose two rows are identical. So we will consider a matrix which is n by n matrix, and it has two rows somewhere which are identical. For example, suppose that this is a row. I am not written, but suppose that at ith position there is a row Ri, and there is another row at jth position which is Rj, and we suppose that these two rows are identical. What does that mean? Ri and Rj are the same. This is what we are going to suppose. And we have to prove that the determinant of this matrix is 0. Then what will happen? If two rows are identical, then if we swap these two rows, then there will be no change. Why? Because if you swap this row with this row, you are actually swapping Ri by Rj. But in other words, Ri and Rj are both different. I mean, both are same. So, since these two rows are same, so after swapping there will be no change in the matrix. So the determinant should be the same. But on the other hand, because of the rule says when you will swap the rows, then we will get determinant of A is equal to determinant of the negative of the determinant of A. This is the rule. The rule number 1, which is here, you can check. Whenever you swap two rows Ri by Rj, the determinant will be the negative of the determinant. But here, the new matrix and the old matrix are same, so A and A prime are the same. So determinant of A and the new matrix is also the determinant of A, because after swap we have no change because both rows are identical. So we have found that determinant of A is equal to negative of the determinant of A. But if we take this thing to this side, because this is negative, if I take to this side, it will become plus. So, and here I will get 0 because I have taken everything to the left hand side. So I got determinant of A plus the determinant of A equals 0. If I add these two things, because this is 2 times, so I will write 2 times the determinant of A. Since 2 is not 0, so that means determinant of A is 0, hence it is proved. So this is what we have to prove. Now look at the second consequence of these row operations on the determinants. The second consequence is, if rows are linearly independent, then the determinant of A is 0. So in this consequence, we don't know what is the linearly independent rows. So I will tell you, but let's look at the proof. We will suppose that there are two rows which are linearly independent. Then I'll tell you the definition of linearly independent rows. Suppose that there are two rows, the last row is linearly independent on the other rows. So since we have n rows, so since the last row is depending upon the others, so that means Rn, that means the last row, is depending upon the previous rows. You can check Rn is equal to the previous rows means R1, then R2, then R3 up to so on, then Rn minus 1. So the last row Rn depending upon the first n minus 1 rows. There are total n rows. There are first n minus 1 rows and the last row is nth row. So the nth row is depending upon the previous n minus 1 rows with the coefficients alpha 1, alpha 2 and alpha n minus 1, so on. This is the definition of linearly dependent rows. So that means since we have assumed that Rn depends upon the previous rows, so we will use this thing to prove that the determinant of the matrix is 0. Since this is an equation, from this equation if I take Rn to this side, here I will leave 0, right? What does that mean? That means this is as it is. You can check. This is as it is, everything until Rn minus 1. But this Rn goes to the right side. And here we left with 0. Okay. So this means if I apply this operation on any row, I will end up with 0. So this is very important operation. We can apply this operation on the last row. What does that mean? If the last row is interchanged by this new operated row, but this operated row is 0, so that means if I interchange Rn by this new operated row, then the last row will become 0 because this thing is equal to 0. Since the last row is 0, so that means if I apply the third rule, here is the third rule. Here is the third rule. If I interchange Ri by the combination of any other rows, here we have 2 rows and here we have n minus 1 rows. There is no problem. So if I apply this, the last rule, then it says that the determinant will be unchanged. There will be no change in the determinant. Hence, we can check that determinant of A is the same as the new determinant of the new matrix. Okay? But if we expand the determinant along the last row, since last row is 0, so if we expand the determinant along the last row, everything will be 0. Okay? Along the last row, the determinant will be 0. Hence, it is proved that whenever you have two dependent or linearly dependent rows, then the determinant is 0. Look at the last consequence. So the last consequence is for the triangular matrix. Triangular matrix means there is something in the main diagonal, and either the above the main diagonal or the main diagonal, everything is 0. What's that means? Here is the matrix, here is some diagonal. Either everything here is 0 or everything here is 0. Okay? So if everything here is 0, then it is called lower triangular matrix. If everything below is 0, then it is called upper triangular matrix, right? So we have two kinds of triangular matrices. So if everything above or below the main diagonal is 0, then it is called the triangular matrix. So for the triangular matrices, the determinant of a matrix A is the product of only the diagonal entries. What does that mean? This is the matrix. For example, here are diagonal entries some whatever they are, I don't know, up to so on. And here you have anything. For example, here you have anything, and here everything is 0. Then the determinant is only the product of these diagonal entries. These entries, whatever they are, will not affect the determinant of the matrix. This is very beautiful thing. Okay, so this we will prove this last consequence. Let's look at the proof. Since the row operations can be used to convert the triangular matrix to the diagonal matrix, so we can have the determinant equals the product of the diagonal entries. What does that mean? If you have, for example, the upper triangular matrix, for example, here you have something A11, A22, up to so on, ANN, and here everything is 0, everything, and here you have anything, I don't know what is here, anything. So since this is the pivot entry, everything below the pivot entry is 0, and the next pivot entry is this, everything below this is 0, but above is not 0, but I can use the row operation to make this entry 0. Similarly, the next pivot entry is here, which is not 0, but the below everything is 0. You can use row operations to make above also 0. So after row operations, I can end up with a matrix which has only the diagonal entries and all other entries to be 0. This kind of a matrix. So whenever you have a triangular matrix, so after applying the row operations, you can always end up with a matrix which has only the non-zero diagonal entries and all other entries are 0. These kind of row operations have been already used in the previous videos. You can look at those. Now, what is the determinant of this matrix and this matrix? Since we have used only row operations and we have not swapped anything and we have not multiplied any row by any matrix, we have just applied the row operations. So that means the determinant of this matrix A and the determinant of this matrix A prime, this is the matrix A prime, both are same. So if we calculate the determinant of this diagonal matrix, that means that is the same as the determinant of this matrix. How to calculate the determinant of the diagonal matrix? So first of all, we will expand the matrix along the first row. So what will happen if I expand the determinant along the first row? Since in the first row I have only this non-zero entry A11, if I skip this and skip this, I will end up with the determinant of this submatrix. So I will write the determinant of this submatrix, and since all the other rows are all the other entries in this row are 0, so I will not write any other thing. So now this is A11, I mean the first diagonal entry, and from in order to calculate the determinant of this, I will expand this determinant along the first row. So I will do the same thing. What will happen? I will write this A11 as it is, and this row as it is, this entry A22 as it is. The determinant of this submatrix. How to write this determinant of this submatrix? In this way. And similarly, you will carry on this process, A11, A22, and then you will get A33, and then you will get A44, and then you will get ANN. What does that mean? A11, A22, A33, ANN, up to so on. So these are all the diagonal entries. Since there is no other entries, so there is no effect of the other entries. So we have proved that the determinant of the triangular matrices is only the product of the diagonal entries. And the same thing you have checked that at the end we have only got the diagonal entries of the matrix. So we have proved this property.